Good morning. How are you all doing? Hands up anyone who's got a party hangover. That's great. We should celebrate software and coding and development and all being together like this. And I'm going to talk to you now for an hour or so about architecture, the stuff that's hard to change. This is me, Beattie. I'm CTO at Skills Matter in London. I'm a Microsoft MVP with the Visual Studio and Developer Tools program. I run the .NET user group in London. I created a programming language called Rockstar so that everyone can be Rockstar developers. And I have some Rockstar swag to give away, which I don't want to take home, so come and grab some at the end. And about 5 or 6 years ago, the company I was working for hired some consultants to restructure things. And one of them had a long series of interviews with me and said, we think you'd be better suited as the systems architect. And so I get this email, Dear Dylan, this is to confirm your change of job role to systems architect. You are now responsible for architecture. Architecting, doing architect stuff, systems architecture, and architecting systems. Congratulations. And so I go back to my desk and I sit down and I go, hey, I'm an architect now. It doesn't feel any different. Visual Studio still doesn't load very fast. You know, and that started me on this journey of, it's like, if I'm going to do this job, I want to do this job well. So I want to understand, what is architecture actually all about? What does it look like when you do it well? What's the role of an architect on a good team? And I sort of started off by digging a little bit into the words we use. Because we have all these words we use in software that we kind of steal from elsewhere. Like, we talk about pythons and mice. And people are like, yeah, I have a Python in my house. I feed it mice. It's like, no, Python and mice are different. And we have buses, and we have pipelines, and we talk about launching and crashing. And, these are all English words which mean something else. And we've taken them and gone, no, we're going to use them to mean a completely different thing. And this, language can be a really powerful way of understanding the approach people have to problems. There is some controversy in the world. So put your hand up if you're a developer. You call yourself a developer. Keep your hand up if you call yourself a hacker. Coder, architect, front end, back end, engineer. The word engineer is this controversial term. We talk about software engineering. Now, there are some countries in the world where you are not allowed to do that. In Canada, you are not allowed to be an engineer unless you have an engineering license from the Canadian government. In New Zealand, you can be an engineer if you have a degree in software engineering, but not if you have a degree in software development or computer science. You have to have engineer in your degree. I live in the UK, and a couple of weeks ago, the cable TV in my house went out, and they sent an engineer to fix it. And I was like, I do not think that this person has an engineering degree, But we have these ideas about architecture and engineering. And, my very first job years ago, I worked for Arup, who are a big construction company. And they have architects and they have engineers. And I sort of started digging a little bit into where these roles come from. And the distinction that kind of makes sense to me, let's think about construction for a minute. We have these two things here. The little barbecue on the left, that's a hack. Like that, probably the person who designed that built it by themselves. Or they got a couple of friends in to help with them. The thing on the right is the Brooklyn Bridge. The guy who designed the Brooklyn Bridge did not build it by himself. Now, and this I think is an interesting distinction. Architecture maybe is the point where you're involved in designing software that you're not actually going to write. Like you're coming up with the designs and the interfaces and the structures, but you're not going to be the person actually writing the code. And in building architecture, we have these amazing examples that we celebrate, and people travel all over the world to go and look at these kinds of things. And in software architecture, we're a little bit behind the curve on that. When was the last time you showed someone a code base and went, look at this, it's absolutely beautiful? No, come and look at it from this side. Here, take a picture. Maybe architecture and software is not quite the same as what the rest of the world thinks of architecture as. And it's only software and buildings that have architects. There aren't airplane architects, there aren't racing car architects or plumbing architects, Now, let's dig a little bit deeper, because the first person to use the term software engineering was this lady. Anybody know who this is? You should. She's awesome. It's Margaret Hamilton. She was the lead engineer on the guidance systems for Apollo 11. And she was the first person to talk about software engineering and what she called taking a systems view of how software works with all of the other components in a system, which in this case was the system that took Neil Armstrong and Buzz Aldrin and landed them on the moon. She was the first person to talk about software as an engineering discipline. It's not something you do off to the side by yourself. It's something that has to fit in with all of the other processes and machinery and systems that are happening to make this project work. The first person to use the term architecture about computer systems was Fred Brooks. He wrote the Mythical Man Month, which I'm sure some of you have read. Very, very influential engineer and scientist. And way back in the 1960s, 1962, he was working on a system for IBM called Stretch. And in the prelude to that, he has this quote: "Computer architecture, like other architecture, is the art of determining the needs of the user of a structure and then designing to meet those needs as effectively as possible within economic and technological constraints." First time the word architecture was applied to computer systems. Now, back in the 60s and 70s and 80s, computer architecture almost always meant hardware, because hardware was the stuff which was expensive to change. If you decided to change the way a piece of code worked, you just wrote some new code and you shipped it and you were fine. But there are fundamental decisions. One of the decisions that Fred Brooks made on the IBM Stretch project was to use 8 bits in a byte instead of 6. And basically, you can trace almost every computer since then. The 8-bit byte convention that all of us use, you can trace back to this decision. Now, you imagine changing that decision halfway through building a computer system. It's like, all right, that's it. Throw away the processors, throw away the motherboards, throw away the buses, throw away the factories that we've built to create the motherboards and processors. We got to start the whole thing all over again. Expensive to change. Software was always cheap as a percentage of the whole cost of building a system. 2 things happened around the 1990s which started changing the way we think about this. The first of them was business software went mainstream. Companies who had, never ever had computers before, suddenly they had computers. And they were getting people to build software for them in Visual Basic. And, little companies, florists and little hotels and, car wash places were hiring somebody to write them a little piece of software. And they set it up and run it, and it would be great, and they could print your invoices and stuff. And then a couple of weeks later, they'd be like, oh, it doesn't do this thing we need. We need to change it. How much? And suddenly the cost of making changes to a software system became a significant proportion of the investment for a lot of these businesses. And so we started thinking, what is it going to cost to change software we've already created? The other thing that happened was the World Wide Web. Up until this point, pretty much all software ran on one computer, and if it had any output at all, it was a screen or a printer. We didn't really do email, we certainly didn't do apps and APIs and uploading and stuff. The World Wide Web came along, and suddenly, instead of building software that would run on one beige box in an office, we're building stuff that runs on thousands of machines all over the world, clients and servers and gateways and all these components. And there are companies now for whom the cost of changing software is almost their entire operating budget. They have a couple of janitors and some HR people, but almost the entire payroll is just people who change code all day, every day. And for those companies, if those changes are cheap, they're profitable. If those changes are expensive, they're in trouble. And so we kind of hone in on this idea of architecture as being the stuff that's hard to change, because everything else is just coding, right? The first kind of formal treatment of software architecture was this book, Mary Shaw and David Garland, which was published in 1995. And one of the things I love about this is they called it an attempt to formalize a substantial folklore of system design. There are all these people all over the world having good ideas about how to build bigger systems, faster systems, scalable modular computer systems. But no one had ever kind of brought all this thinking together and gone, let's try and get some words on this so we can have conversations about how to do all this stuff better. I want to dig into Fred Brooks' definition a little bit because I like this, and I want to break this down into 3 things. So, architecture, determining the needs of a user, designing to meet those needs within economic and technological constraints. Now, one of the big revelations for me in my journey to becoming an architect was realizing who the users were. Because we build computer systems, right? And we think that the user is the person on the other end who's dragging and dropping and filling in forms and all this kind of stuff. When you're an architect, who are your users? They are the developers on the team. Your job is to serve the needs of the people who are going to be building and shipping the systems that you're working on. And it's not just the people who are on your team today, it is the people who you are going to be hiring next year, or the people who are going to be working on your open source projects in 3 or 4 years' time. And so your role is to think about, how do I serve people we haven't met yet, building software we haven't written yet, to sell things we haven't thought of yet to customers that we haven't got yet, and make them all happy. Easy, right? We're probably going to need a plan. Now, plans have had a bit of a rough time when it comes to software engineering because of this wonderful thing called the Agile Manifesto, which everybody jumped on and read and went, this is brilliant. Now, not a lot of people know this, but René Descartes, the French philosopher, was actually an Agile consultant on the side when he wasn't doing philosophy. And he's working with a client one day, and he says to them, you know, the Agile Manifesto says that we should respond to change instead of following a plan. And the client says, oh, that's brilliant. We haven't got a plan. And Descartes goes, sacre bleu. If you don't have a plan, how can you choose not to follow it? It's not a valid choice. There is a difference between saying, this is our plan, but circumstances have changed. The plan is no longer accurate, and just going, we haven't planned anything, let's just make it up as we go along and see what happens. What the authors of the Agile Manifesto had observed time and time again is teams deliberately doing the wrong thing because that's what the plan said. And that was what they were trying to address when they wrote this. We are uncovering better ways of developing software. Through this work, we've come to value responding to change over following a plan. While there is value in the items on the right, we value the items on the left more. You need a plan. But the plan is not guaranteed to be accurate. The plan is a living document. You as an architect need to have some idea what it is you're going to be trying to do and how those things fit together. There is another detail in the Agile Manifesto, or one of the principles behind it that I just wanted to bring up. We follow these principles. The best architectures, requirements, and designs emerge from self-organizing teams. Now, the point that they're trying to make here, if you have a team of people who are working well together and are coming up with their own way of doing things, step back and let it happen. Do not hire people and go, there you go over there and self-organize. And then you come back in a month and you're like, where's the project? And they're like, we self-organized into the bar across the street. What do you want us to do now, you know? Be prepared for this to happen, because high-functioning teams will click and they will start this positive feedback loop. But if your team come to you and say, we could use some help, you know, we're not sure how to approach this, we don't know how to collaborate on this, you need a better answer as an architect than just, yeah, go and self-organize. It's fine. You need to give them the support to allow these things to emerge. Let's talk about constraints. Here are the rules. No new hires, no JavaScript, no open source, no Microsoft, no cookies. This, I believe, is the engineering principles of the Oracle Corporation. We're not going to work here. This would suck. But everything you do, there are going to be constraints. There are going to be things you just cannot do, you know. We cannot yet beam solid objects around the world. If someone comes to you and goes, can we build a teleport thing for shrimp? You'll be like, no, that's not a thing. Sometimes they're going to come to you and go, can we do high definition like video calls in real time without using wires? And for a long time you'll say no, 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 no. And then one day you'll be like, actually, maybe, yes. For a long time, everybody believed that a touchscreen phone was going to be a disaster because all the touchscreens anyone had ever seen were those plastic things in the airport that don't work and they click in the wrong place. And there was a team of people working at Apple who were working on all these different things, different kinds of glass, different kinds of touchscreen displays, multi-touch. And they were the people who everyone else was going, a touchscreen phone is impossible, the constraints are too big. And they went, actually, no. Now it's possible. Now we can do it. And they launched the iPhone, and within a year, everyone was going, yeah, of course everyone wants a touchscreen phone. You know, we'll do one, we'll do one. Google did one, Android did one. All of these different things converged. Sometimes as an architect, your job is to keep an eye on everything that is happening so you can come to the table and go, the thing we thought was impossible, maybe now is the time. One of the things about this job which is difficult is communicating those constraints to the developers. All your developers, they go to NDC, and they go back to work and go, new shiny JavaScript framework's going to solve all our problems, and you're the one who has to say, sorry, we have to support Internet Explorer. That is one of the constraints of what we're doing, because this is a business, we have a big client, they're still using IE9 or God help you, IE8 or something. And you're the one who has to communicate those constraints and explain to people, yeah, I know you want to do it this way, but that doesn't actually align with the constraints of the system that we're designing here. So there we go. Determine user needs, meet those needs within economic and technological constraints. Now, actual doing software architecture is really easy. You just got to do 3 things. You got to make a decision, communicate it, and then reinforce it. Thank you very much. Bye-bye. No, I will do some more. So, making decisions. How do you choose? Someone comes to you as the architect and says, we want to build a system that does this. We want to decouple like a login system so we can build different microservices that use common authentication. How can we do that? And your job is to come up with a way of doing it. And before you can do that, you need to understand 5 things. First of all, what have you got? Now, a lot of time in organizations and software teams, there will be 2 versions of the truth. There will be what people think they have, because they paid someone a lot of money for a high-performance transaction processing system, and there will be what they actually have, which is 100,000 lines of Ruby that doesn't work properly, you know? And you need to understand these disparities. Now, the best way I've found of doing this is to look at the borders, the boundaries between the different systems. You want to understand the traffic that is flowing between the components of these systems. Don't worry too much about the code. Don't worry about the spec. And when people tell you what something does, take it with a pinch of salt. It's useful, but it might not be 100% accurate. Here is the simplest possible systems diagram I can think of. Now, as an architect, you don't care whether that website is PHP or .NET or Perl or Ruby or whatever. And the internet, that's someone else's problem. But this thing in the middle, HTTP, how many questions can you ask about that? How many transactions does it cope with? Is there HTTPS on it? When does the certificate expire? Does it cope with get, put, post? What if I put a proxy in there? How much of this stuff can we cache? Are we using e-tags on the traffic that flows across it? Just by putting a network trace on that HTTP and watching it for half an hour will tell you more about how this website actually works than any number of hours spent reading the code and going, oh, this module looks interesting. Oh, it's never been run. We don't know why it's here. Traffic is real. Traffic is the lifeblood of living systems. You don't care what anything was designed to do. You're Gene Kranz in Apollo 13. You care what it can do. You need to understand the actual capabilities of the systems, not what was in the spec. And sometimes this will be disappointing, like our high-performance authentication system can only cope with 6 users a minute. Sometimes it'll be pleasantly surprising. You'll dig into AWS and be like, there's a whole Redis cluster in here that I didn't know we had. This is brilliant. We can start using this to speed up all kinds of things. We can put Varnish in front of our web server and boom, instant acceleration, and we can start rewriting stuff. There will be pleasant surprises as well as disappointments. It's well worth taking the time to do this. Of course, some of you are going, well, we're working on a greenfield project here. We don't have anything. There is no such thing as a greenfield project because there are always going to be a couple of little systems scattered around the landscape. Maybe there's some sales data in an Excel spreadsheet that you need to work with. And some of this you'll be able to work with, and some of it you won't for complicated reasons. There will be the wreckage of the last attempt to build the greenfield system because somebody has always tried this before and there'll be some code kicking around. There will be politics. There will be the person who got fired for choosing to use Microsoft SQL Server, and so now no one will touch Microsoft SQL Server because the last person who did it got fired. And you're like, no, okay, I'm really glad we know that because now we know how to approach those kinds of conversations. There will be the rabbit hole, the thing that looks really, really easy, and you say to your team, yeah, just integrate Redis with Nginx, and they come back 3 months later and they go, boss, we really need some. This is not going how it said it would in the documentation. All of these things are out there, and only once you understand them, you know where they are, can you really make informed decisions about how to approach what you're doing. You know what you got. What do you need? You got most business stakeholders, they say, yeah, the website needs to be fast, website needs to be secure. You say, brilliant, thank you for the briefing. You go to your team, hey, boss wants it to be fast. The team go, brilliant, we'll build our own HTTP accelerator. I saw a conference talk about it. And you go back 2 weeks later and the boss says, is the project finished yet? And you go, no, the team is working on an HTTP accelerator. It's really cool. They're using bitwise pattern matching on the incoming network stream to get a top 10 of the fastest web servers ever. And the boss goes, not that fast. How fast? Turn these into business conversations because as the architect, you're going to be the conduit between what does it mean in tech and what does it mean in reality. How fast is a fast website? 500 milliseconds response time for 90th percentile. Some stakeholders will be, that sounds brilliant. Some will be, what's a percentile? You sit them down, you go, okay. What this means is if 10 people are on our website, one of them's going to have to wait a little bit. And they'll say, how long? And you say, I don't know, 1 second, 5 seconds. And they'll, yeah, 5 seconds is too long. No, we don't want that. So you can turn this into a conversation. And they come back and go make it faster. And you say, well, that's going to cost. And they say, how else can we make it faster? And you say, we could take off the JavaScript that draws the banner adverts. And they go, we can't do that. And you're like, well, do you want it fast or cheap? You can't have both, you know. Turn these into business conversations. They say it needs to be secure. How secure? You know, go beyond just it needs to be secure. What is the threat model that you're worried about here? There's a great talk I saw James Mickens give here a couple of years ago, where he was talking about basically 3 different threat models, which are Russian botnets, your angry ex-partner, and Mossad. And Russian botnets are going to knock on the door for 3 seconds, and if they don't get in, they're going to move on to the next account. So, you know, they download these huge tables of passwords from the Pirate Bay and that kind of stuff. That's one threat profile. The angry ex-partner, this is a difficult one because they probably have access to the cell phone that belongs to the account, so two-factor authentication might not work. So think of mechanisms for working around that. Mossad are already in your system, just stop worrying about it and enjoy your life and don't piss them off. What can you build? If you decide, right, we need to do this, this is what we're shipping, how dependably and reliably can you hit those targets at your sprints or your iterations or your stand-ups or whatever cycle you're using to do this work? And this one boils down to what I call 4 Ps. People, patterns, packages, process. Who are the people on your team? And who are the people you can hire? Which communities is your project interesting to? Are there people there you can reach out to and get them involved? You know, how easily, what kind of skills have you got? You got Angular people, F# people, React people, back-end, front-end. Understand all of these and align them with the kind of work that you're doing. Make technology choices based on who you've got, based what you can do, who you can hire. Patterns are the kind of conceptual building blocks of modern software, and some patterns fit very well with some people using some languages, and some don't. I've been doing a lot of work in Ruby on Rails recently, and Rails is so tightly coupled to the MVC pattern that we had a 10-minute conversation the other day about something that they called a service object, and I was like, what is a service object? Eventually I worked out they're talking about classes. Just, you know, classes, behavior and data and a thing. And Rails is so coupled to it's a model, a view, or a controller that something that isn't one of these things has a special name. Whereas in .NET, we start with everything's a class, and then you're like, oh yeah, and if your class does this, then it's probably the controller pattern. Understand the relationship between the patterns and the technology choices you're making, because that can make a huge difference, especially if you find yourself fighting the language or the framework's opinions about the patterns you should be working with. Packages. All languages now survive in a sort of ecosystem of components and libraries and modules, and you need to encode a transparent PNG or do some crypto or stream some video. For most languages, you'll be able to find someone who has already solved this problem. Understand the breadth of the ecosystem that you're choosing to work with. How easily can you get those packages? Are they actively maintained? What happens if one of them goes away? How easy is it to fork and do your own thing? And process is just about reproducibility. It's about being able to sit down on a Monday morning and say, we're going to ship this by Friday, and on Friday, most of the time, you've done it. It's about how your people collaborate together. It's about how well you understand the pitfalls and the capabilities of the systems that you're working with. What can you buy? There is a rule. Dillon's law of software, never use PowerShell when you could use MasterCard. Your team should be building the things that you can sell, the things, or the things you can give away, the things that create the value for your organization. Don't create your own cloud system. Amazon have done that. Unless you are trying to compete with Amazon in the cloud infrastructure space, that is a waste of your time. They solve that problem, you solve your problem. Look at everything you're doing. Now, there is a point here. I had a really interesting conversation about using Google Analytics, because one of the systems that I'm working on has its own tracking and analytics engine. And the reason for that is that we are using those analytics as part of the product. And someone said, why don't you just use Google Analytics? And I said, because we don't want to rely on Google for something we are actually providing to our customers. This is what we do, we're delivering it, we own the value stream for that. For seeing how many people clicked on an email, yeah, we have Google Analytics for that, that's fine. There's this sort of, yin and yang, there's this balance here. What can you lose? Raise your hand if there is a system in your company that sends email. Keep your hand raised if there are 2 systems that send email. 3, 4, 5. I once did an audit. We wanted to rebrand the outgoing email to fit the new corporate color scheme. I found 15 different places in code where a developer had written some code to create an email message, template it, populate the HTML, and send it. And the first person who did this was definitely me, because nothing existed, and I sat down and went this. The second one was a developer who didn't know that I'd already done the first one. The third one was somebody who went, well, 2 people have done this already, so clearly that's how stuff works around here. The fourth one was an outsourced, and I had to go to them and go, look, making the emails purple is actually going to be really complicated. We've turned the color of an email into a software architecture problem because we have this duplication. So what we actually did was, in the process of turning it purple, we consolidated all of our email into an outgoing relay service that applied the branding at the perimeter before it got sent. Look for that kind of duplication, because there's going to be opportunities to make things easier, streamline them, recover some technical debt, just improve the cost of changing those things. Once you understand these 5 things, you've got to decide what to do. Now, this is kind of the easy part, because once you've been through all those motions, you've had the conversations, you've talked to the teams, you understand the landscape, you come to things like NDC and you kind of keep up with what's going on in the industry and the community, a solution will emerge. You'll have a couple of good ideas, you'll bounce them off some people on your team, you'll be like, I think we should do it this way. Then comes the really fun part. You have decided what the software is going to look like, and in your head is this beautiful, crystalline structure of data flowing through systems and interfaces and data structures and lambdas and serverless and cloud, and you sit down with your team like, let me show you how the software is going to work, and you draw them the diagram and they look at it and they go, what? Is that Java? I'll talk about the problem with diagrams. Now, in construction engineering, you hire someone to build you a building. They will start by making some drawings. And you'll look at the drawings and you'll be like, all right, I'm sure you know what you're doing, and they'll give you some more drawings. And they will produce drawings of end elevations, side elevations, plan views, schematics. But sooner or later, they will come up with artist's impressions, visualizations, and you'll look at that and you'll go, okay, I can see where we're going with this. And they'll come up with slightly higher fidelity versions, and you'll think, okay. And then they will build the building, and you will go, it's exactly what I thought it was going to be. And you can look at it, and you can look at the drawing, look at the building, and go, yeah, did it, nailed it. That's exactly what I expected. Now, we grow up surrounded by drawings. One of the earliest things that we learn to do as children is draw, to communicate by making marks on pieces of paper, and your parents stick them on the fridge and hope that you get better at art before it gets embarrassing, And we get good at reading. We have picture books as kids with pictures, and we match the pictures to the words. So we are visual creatures who grow up surrounded by diagrams and drawings and photographs and illustrations that we kind of intuitively know how to read and get meaning from. Unfortunately, in software, this is not necessarily true. Here is a software architecture diagram. Who wants to go and build this for me? No, this is a formal notation. This is a diagram drawn using a notation you can learn in school. I studied this at university. This is the Jordan DeMarco notation for software engineering. Who can tell me what the things on this diagram are? Anybody? Nobody.
The thing on the right is a regex.
No, it's not. The slashes are the wrong way around. The thing on the right, well, for starters, let's add a key for people who might have forgotten a little bit of Jordan DeMarco since they were in school. So there we go. There's the key to the Jordan DeMarco notation. So the thing at the top right's not a regular expression. It's a database or a file system. We don't know which, but it's a database or a file system. And the oval things there are functions. So now you can look at this and you can be like, okay, so we've got some these 2 things that have got data in them, and then they're going through these 2 ovals, and then there's this bottom right thing. What is that? Okay, that's input-output. And for some reason, it's called mandrill. And hang on, I think I might know what mandrill is because I remember reading about it in the MailChimp documentation, so maybe it's that. And this thing with the //, maybe that's a Windows file share. It's got $1 on the end, could be. Let's start decorating this with some more detail. So first of all, internal code names. Let's just put quotes around them to say, don't bother Googling this, you ain't going to find anything. Excelsior is a SQL server full of customer details. Why is it called Excelsior? Because the person who built it got it out of Excel. I don't care. Naming is hard. Mercutio, what is it? It's a .NET service that populates email templates. So Norman is a .NET app that sends emails. Why? Norman Mailer. Okay, thanks, Steve. Really appreciate that. This thing over here, JK6GB87, that is the Dell asset tag of the server where the marketing department keep all their email templates. All these things are real, by the way. These are actual bits of software that I've worked on. And Mandrill is the SMTP relay service for MailChimp, which is an email platform. So now we're kind of getting, like, we're still not sure, but you could sit down and go, okay, I think I understand the kind of people we're going to need to build this system. We're still restricted by the fact we're using Jordan DeMarco notation because we got it out of a book, and that means the only things we can conceptualize are databases, functions, data flows, input, outputs. Scrap it. Let's come up with our own notation. Nobody can read it anyway. We're going to have to include a key. Boom. Now we're getting somewhere. We've got some clip art, and we've got some Microsoft Office templates, and we've got some stuff we found on Google. We've got this red line here with the boxes on it, which I cribbed out of the RabbitMQ documentation. So now we can be like, okay, this is cool. We got Excelsior. What is the green line here? That's ADO.NET. Okay, this makes sense. We got Mercutio. What's the little gear wheel? Okay, those are Windows services. That blue thing there, that's an SMB file share. Okay. And we're starting to think, okay, I understand now. Like, you can look at this diagram, see what kind of things you're going to have to do to deliver it. Let's go even further. Let's annotate the traffic boundaries. ADO.NET, okay, Windows authentication. Now we know how to plug these things into each other. This Windows file share we're using for text and HTML. This RabbitMQ, okay, that's Cloud AMQP. Brilliant. We know how to work with that. SMTP port 993 TLS enabled. That's why I can't send any email. I'm using the wrong port and I don't have the certificate. Now we have enough information here to actually have a meaningful conversation. How are we going to build this? How long is it going to take? How many instances do we need to provision to run it? The one on the left looks like the ones in the textbooks. It is neat, and it is elegant, and it looks like the work of a professional, and the people reading it go, I'm not going to ask about that because I don't want to look stupid. The one on the right is starting to look like a bit of a mess, but it's a mess which has useful information in it and you can actually use to have a conversation. One of the big challenges that I find in all kinds of software development is the examples in the books and the tutorials and the conferences are always tiny. No one ever shows you how messy this stuff gets when you do it for real. This is one part of a systems architecture diagram that I built as part of a outsourcing collaboration project about 5 years ago. And this, is literally broken down. There's a key on here. Like I said, this is all the different kinds of traffic. There's even a color code in there for some hideous VB cursor-based library. We knew that existed. The network traffic made no sense, but we knew it had Visual Basic on one end and SQL Server on the other. We could never make any sense of it, so we capture on there, look, this thing's here, it's important, but abandon hope, you're never going to find out how this thing works. And just stick, arbitrary notations. Like there's a comment on here, database sync every 5 minutes, updates, usernames and passwords. You can do it on demand by pressing the big red button. Put that kind of it, because this is something people are like, all right, it's already messy, what if we scribble on it? Let's start making notes and annotating and moving things around and stuff. And this is what diagrams look like when you actually try and convey reality instead of trying to make things that look good like they did in the engineering textbooks. Final note about diagrams. Here are two software architecture diagrams. One of these is the hexagonal architecture. Which one? I'll give you a clue. It's not the one with the hexagons on it. A lot of the time, there will be words like hexagonal architecture, N-tier, ports and adapters, layered interfaces, that kind of, if you've heard the expression hexagonal architecture and you look at these diagrams, you will logically assume that the one with the hexagons is hexagonal architecture. Now, we use the name hexagonal architecture because the first version of the paper about ports and adapters used hexagons in the diagrams and the name kind of stuck. It's got nothing to do with hexagons. There aren't necessarily 6 of anything in a hexagonal architecture. It's just a name we got. The thing on the left with the data ports and the adapters and the file stores, that's hexagonal. The thing on the right is a honeycomb with clip art pasted into it. It's nothing to do with software. I made it up. Never be afraid to ask. Never be afraid to say, hi, I'm sorry, I'm still not clear. Can you just run through what that thing on the diagram is one more time? What does this line here do? What are these things? The yellow thing, is that a SQL Server database? By having these kinds of conversations, one, it makes it okay for the other people in the room to be like, actually, yeah, I don't understand either. Can we do that again? 2, it gives the architect the context of like, okay, next time I present something, these are the things I want to cover in advance so that we can cut straight to what are we going to do and how we're going to build it. It's all about reinforcing decisions. So you've come up with your design. You understand the constraints. You know what it is that you're trying to deliver. Now you want to help the team build the right thing. I did initially call this enforcing decisions, but I kind of didn't like the kind of, the architect as police kind of deal. You want to support your team in the work that they're doing. And this boils down to two different kinds of things, what we call validation and verification. Validation, are we building the right thing? This is hard because what you can do is come back in 10 years and see whether this company's still in business and the software worked. There isn't really a shortcut for this. But verification, are we building the thing right? Is the thing we're creating, does it match and reflect the ideas and designs and structures that we've talked about? Now, with construction architecture, you can take your diagram, and you can take your building, and you can look at them side by side, and you can go, yeah, that looks right to me. And there are other dimensions to it, engineering stress diagrams and load-bearing things and stuff. But this technique we developed as kids of looking at a drawing and telling whether it looks like real life or not, that holds us in good stead. So let's do the same thing with some software. Here's our diagram, right? Teams built the code. It's done. It's shipped. We want to have a look at it and see if it looks like the diagram. How do we look at the software? I know. Microsoft Azure has a dashboard. Let's look at that. It was very pretty, but it doesn't really look like the diagram. Maybe TeamCity can show us what's going on. Nah, still pretty, but it doesn't really help us, and these red bits might be bad. I know, we'll look at the code. Nah, I'm just not seeing the relationship here. How can you tell whether the software that has been built matches the design, the architecture, the concepts, and the structures and things? Now, when I first started out doing this, I made a classic mistake, which is I'll do all the code reviews. So all the teams can build what they want, and then as the architect, I'll review the code, I'll read it, I'll make sure that it's right. This really, really sucked, and it was horrible, and I do not recommend you ever try it. One, you'll burn out. You'll have days when you're still at work at 7 o'clock, at 8 o'clock at night, and you're like, oh, there's 15 pull requests still to review, but if I don't review these, nobody can do any work tomorrow. And so you just kind of get sloppy, and you're just like, yeah, that kind of looks right, I don't know. The other thing is it restricts the ability of your teams to do stuff that you don't understand, and you get this. I reviewed your C# code, and I still don't know what it does. And your lead engineer says, dude, my team's using Scala. The other problem with reviewing the code is, let's have a look at this code here. Now, we've had a meeting about the architecture and the design, and we've said we're going to use a repository pattern with an identity map. And everyone has gone, oh, repository identity map. We understand, Mr. Architect. Thank you very much. And then they give you this code. What can you tell from this code? You can tell that the developers knew that the word repository and identity map were important, and they should use these names. The names don't tell you what the code does, they just tell you what somebody called it. Reading code and trying to distill what it does, on a good team who use naming consistently and who kind of understand the relationship between patterns and classes and naming and stuff, it can work. But it can also be a bit of a minefield. It's like wandering through a city at night and going, ooh, luxury hotel, that looks pretty good. And then you wake up in the morning and you're like, okay, maybe following the labels was not the best way of understanding what we were doing here. So what can we do to kind of gently guide our teams down the correct path? Create a pit of success that will help them come up with the right kind of implementation. One of the most powerful things you can do is to exploit something called Conway's Law. Teams that build systems, the system they build will end up matching the communication and organization structures of the teams who built it. So if you have software which is split into components, you want tight-knit teams building a component, and another tight-knit team building another component, and another team building another component. And align them with the technology choices. Bunch of front-end people, okay, you do the front-end. It sounds obvious, but there's places that get this wrong. Front-end team, you're over there. Angular, React, JavaScript, whatever you want to do, that's your bit. You, over here, you're doing F# and calculations and back-end and price quoting, all this kind of stuff. You can even exploit geography to make this happen. Say, all right, well, we've got an Angular team over here in London. We've got a F# team over in Belarus where we've outsourced a lot of the heavy lifting and the processing, and then our Android team is going to be based down in Porto. What you get here is the boundaries between these things will naturally emerge because it's really, really cheap to collaborate, and it's really, really expensive to change something collaborating with a team in another time zone. So you get the boundaries between the teams right, and this is where you as an architect can get involved with this. You have a front-end team. The front-end team are building code that plugs into an API server. Sit with them at the beginning and say, right, what we're going to do here is we're going to fake up some API responses so you can start work. And then the other side, you go to the back-end dev team and you say, right, I'm going to help you build the specifications, the test suite for your API, and then you can go away and build the client that satisfies those requirements. That's how you communicate the designs. You create the data and you create the tests. You work with them on this, and then you let them go and build the actual code. And then you can plug these two pieces into each other, and as an architect, that's where you look at what's going on in the system and look at the traffic. Are you seeing the data structures that you expected to see? Is the latency and the throughput and the volume of traffic the kind of things you were expecting to see? One of the questions that comes up often is, should architects still code? Yes, absolutely yes. Because if you stop coding, your hair goes pointy and they take away all your Def Leppard t-shirts. But don't work on production systems, because what will happen is you'll have a good idea about how to improve the architecture. And sooner or later, you will give in to the temptation, and you'll be like, I don't want to update the diagrams and have a meeting. I'll just do it. And then the team will go, what the hell have you done? And you're like, it's better now. And they're like, okay. And the first time they'll be like, and the second time they'll be like, all right, fine, you do it. And you'll become the bottleneck again. And suddenly you'll be, the architecture has fallen by the wayside. The team will be like, well, you keep changing things, so this is your problem now. We're not working with it anymore. But you have to keep a hand in. You have to keep coding. Otherwise, it's really difficult. One, to just, keep your tools sharp, keep up to date with what's going on in software. Two, it's a great way of establishing credibility and good working relationships. Best way I've found to do this is the architect builds the monitoring systems. You pick people on the teams, you're like, right, I want to take your API, what it's doing, and I want to show that traffic on a big screen on the wall of the office with red and green lights and all this kind of stuff. Let's pair together on building that thing. So you, as a coder, get enough of an insight into how that system works, but you're not responsible for anything that's actually going into production in a customer-facing system. You're building the stuff that runs on the wall. And one, it gives you a sense of ownership. You're like, hey, this is cool. I got some live code in there. Two, you get a chance to collaborate with people, kind of learn from them, share some advice and wisdom. Most architects were pretty good developers before they started specializing in architecture. There's value in that stuff, but just don't let yourself become the bottleneck. The other thing that you can do, a lot of the time, particularly when you make a decision, say to go and use an off-the-shelf service or host something somewhere or integrate with a payment provider, as a business decision, it makes a lot of sense because these things work. But for developers on the team, often that experience sucks because they have these nasty APIs with signed XML crypto signatures and weird sandboxes and stuff. And the developers don't see the business value. I had a real case a couple of years ago where we ported a whole bunch of stuff across from in-house systems to Microsoft Dynamics. And Dynamics, as a developer, it has some interesting capabilities, but there's a lot of things about it which are quite difficult to work with. And the team was getting a bit downtrodden. I went and I said to them one day, do you remember last year, every Monday morning, somebody would spend 2 hours pulling mailing lists out of the database so that the marketing team could send the weekly newsletter? And they all went, yeah. And I went, have you noticed we don't do that anymore? And they all went, oh yeah. Because you lose sight of this stuff. When the business problem gets solved, the developers very rarely see the solution. Your job as an architect is to go, look, no, remember that nasty thing we used to do? We don't do that anymore. This is why. Communicate the value that is being created through these decisions. Pair with the other developers on your team. Build dashboards, build monitoring systems, look at the network traffic. Don't make yourself a bottleneck. All of these kinds of things are the collaboration patterns that you can use to build high-functioning teams, to allow these behaviors to emerge, to respond to change over following a plan. You have the plan, but you're not married to it. If the plan's wrong, you make a better plan. And all of this stuff, there is this classic XKCD cartoon, how to write good code, And you can, okay, well, are we going to do things right or fast? If you do it fast, does it work yet? No, almost, but it's a mass of kludges and spaghetti code. Throw it out and start over. Otherwise, you do it right. Code it well, are you done? No, and the requirements have changed. Do you know how you get good code? Good code happens when good developers look at code and go, I can make this better, and they do. And almost everything that we talk about at events like this, about how to build better systems, the frameworks, unit testing, integration testing, architecture, what we are trying to do is empower that developer to feel confident that they can try out their idea for improving it. Architecture is the stuff that is expensive to change. You get it right, the things will be cheap to change. Those little ideas, little refinements, someone can open a piece of code and go, I think I can refactor this to make this work better, make this fit better. By good architecture empowers people to do this, whole teams to do this over years and years and years. Like I said, it's hard to validate. You come back 5 years later and you see whether it's working or not. If it isn't, gently steer it around a little bit. But like everything else, it's about giving good developers the ability to look at a piece of code, make it better, ship it, and know that they haven't broken anything by doing that. Thank you.